Let's now have a look at the concept of matrices. A matrix, as we can see here, a rectangular array of numbers, or perhaps other entries. And we can see some matrices written here. Now, a matrix has a clearly defined number of rows and a well-defined number of columns. So we see here we have two rows, a top row and a bottom row. We have two columns, a left column and a right column. And we call this one a 2 by 2 matrix. But the one here we call a 2 by 3 matrix because it has two rows and it has 3 columns. So a 2 by 3 matrix here. This one we could call a column matrix because it has a single column here, and of course it has 4 rows. The shape of the brackets is not critical. Square brackets, round brackets, curly brackets, the constructions all mean the same thing. However, one type to avoid is the straight vertical brackets. We'll come on soon to the fact that that means something different. Now, often we use a capital letter for a matrix. We could call this 2 by 2 matrix 2538 as matrix A, and lowercase letters for the entries themselves. For example, the entry in the first row and the second column are 5 here. We can refer to as A 1, 2. At this point, let's see the conditions for two matrices to be equal. For them to be equal, they would have to have the same number of rows as each other. They'd have to have the same number of columns as each other. And corresponding entries must be equal. There's no point in having the same number of rows and the same number of columns if different numbers or other entries exist in corresponding locations. Similarly, there's no point in trying to equate a 2 by 2 matrix with a 1 by 4 matrix. Simply because the entries are the same numbers, it doesn't work that way. It needs to be the same number of rows, same number of columns, and corresponding entries must be equal. Well, let's see an example here. With two pairs of matrices, let's find the conditions under which the two matrices mentioned in each part of the question are equal. So firstly, we have two matrices here. Can those possibly be equal? We note one thing, that both matrices have two rows. A top row and a bottom row. And similarly, both matrices have two columns. A left column and a right column. So there's still potential for them to be equal. But they're only going to be equal if the corresponding entries are equal. So we can say that they will be equal if, well, we need 2 to be equal to A. We will need B to be equal to 5, equate the top right entries. We will need 3 to be equal to 3. Well, we see this one is achieved. And 9 to be equal to D. We could have fallen at this hurdle when we were equating the two entries that were both already numerical, but they are the same number. So they will be equal if A is equal to 2, B is equal to 5, D is equal to 9. Any other combination of A, B, and D, the matrices will not be equal. But they will be equal for the values mentioned here. Part B, it's one of the same matrices again, 2b, 3, 9, but we also have the matrix 2c, d. Well, we note that the one on the left has 2 rows, the one on the right has 3 rows. Those two number of rows are not equal. We conclude that the matrices are not equal. There is no set of circumstances under which those matrices are equal. This one is 2 rows, this one is 3 rows. At this point, we can stop trying to find any circumstances under which they are equal. Those circumstances just don't exist. We could have started by noting we have 2 columns and we have 1 column here. Again, this says that the 2 matrices are not equal, no matter what the other factors are. It won't help. There's no point in considering any comparison between the entries here. It just won't work. Those 2 matrices are not equal. If we have a matrix, one thing that we can calculate is the transpose of a matrix. So to transpose a matrix, we write the rows as columns and the columns as rows. To say we're taking the transpose, we write a little t in this position here, and you can see our first row has become the first column, the second row has become the second column. Alternatively, we could say the first column has become the first row. So this is the transpose of a matrix. The transpose of an m by n matrix will be an n by m matrix. If a matrix has the same number of rows as it has columns, we say it is a square matrix. The matrices A, B, and C here are all square matrices. We have a 2 by 2 matrix, a 3 by 3 matrix, a 4 by 4 matrix. That we will see that there are some matrix operations that square matrices can carry out that diagonal matrices cannot. For example, a square matrix has a diagonal. It has 2 diagonals, but the one running from top left to bottom right we call the main diagonal. We would also have from top right to bottom left, we would have another diagonal, perhaps a secondary diagonal. If we have a matrix which is equal to its transpose, we say it's symmetric. The 2 matrices here, A and B, are symmetric matrices because if we were to take the transpose of either of those 2 matrices, it will be the same as the original matrix. And this manifests itself in the fact that if we were to select, say, an entry, say this 7 here, we will find that the entry across the main diagonal here is also a 7. Sometimes when we see a column matrix, we would use notation that we might consider consistent with vectors. So it might be, previously, we might have met the vector, say 2, 5, minus 2. There is a consistency between vectors and column matrices.